The motivations of the supersymmetries, there are two things. First of all, the extensions of the Poincare algebra. So in the Poincare algebra, there are three kinds of the generator: spin, boost, and the Bohr momentum. And we can add the additional odd generator supercharge, which convert between the fermions and the boson. And such as supersymmetry algebra is some of the extensions of the such as space-time symmetry, which is the including the anti-commutator. And the other motivation of the supersymmetry is the hierarchy problem to resolve the two different scales of the Planck mass scale and the electroweak scale about the Higgs mass corrections by the Fermi loop. And also there are some of the another motivation of the result of the supersymmetry, which is of the dark matter as a lattice state particle, so-called RSP. And also the muon minus 2x double modern laptop violations is the also some of the can be different with the supersymmetry theory. Today's I will focus on the extensions of the Poincare algebra to the supersymmetry algebra, and maybe there are too many calculations today, so maybe only the focusing on the Poincare algebras says as today's topic. So I will calculate sort of the three things. First of all, the generators of the Poincare algebra, derivations of the explicit form of the generator, for the especially this spin and the boost, and I will write the spin and the boost generators in terms of the one quantity, so-called M. And also I will deduce the commutator relation between the such momentum generator and the spin and the boost generator. And finally, I will talk about the Casmir operator, which is the related with the invariant representations of the Poincare algebra. So first of all, the Poincare group, the transformation in the Poincare groups that represents the space-time symmetry. So there are translations for the Bohr vector space-time and the boost or Lorentz transformation and the rotations are included in here. And especially such as the Lorentz transform and the rotations can be written by the some expansions nearby the identity with the antisymmetric parameter. We can show that this W mu is actually the antisymmetric parameters by using the orthogonality or the invariance of the matrix about the rotations or the Lorentz transformation is the same with the inner product space. So this is a matrix in cosmic matrix for the scalar space-time, and if we consider the tensor transformations of such a matrix with the Lorentz transformation, then such a transformation can be expanded nearby the identity. So nearby the identity and antisymmetric tensor, and if we consider the omega is very small, so the infinitesimal expansion, so the order of the omega scales can be negligible, then the two satisfy these equations, metric transform, then the such parameters of omega should be the antisymmetrics about the exchanges of the index. This antisymmetrics properties of the index is quite meaningful if we consider that there's some exchanges of the rotational axis or boost axis, then it means that there are some antisymmetric. So we can start such a transformation, boost or the rotation transformations as a generator form, exponential as a generator form. So there's infinitesimal parameters, also the antisymmetric, the generator with index alpha beta, and these generators will be represented by the matrix in the Lie algebra. So this is included in the Lie group. transformation, and the generators includes in the algebra. So such a generators has some of the matrix elements, so mu news represent the matrix index. So if we expand this exponential nearby the identity, then there are generators and parameters with the order of the omega to 1. Order of the omega scale is reject 3. And we want to make this generator expression the same with the previous one. So we want to make some of the explicit form of the generator by using these conditions. And if we set some of the specific form of the generators like that, alpha betas in the matrix element in terms of the Minkowski matrix and the Kronecker data, then such conditions hold. So in the right hand side, if we insert this explicit form of the generator, because of the delta the Kronecker delta, the index will be the same, and by the matrix, the index will be the low down and they go up. So the antisymmetric properties of the parameter, so it becomes the left hand side. So the explicit form of the rotation and the boost transformations in the matrix elements can be written by the Minkowski matrix in the plus space time. So this is alpha beta is a generator index that mean user matrix element. So if we calculate the sum of each matrix elements for the each generator, first of all, the sparse components, sparse part of the generators, it becomes a spin generator, which is to make the rotation, and the one time component, the one sparse component generators will become the boost generator, which makes the Lorentz transformation. And if we calculate the spin and the boost generators with the matrix representation, it is actually the generator for the rotations and the Lorentz transformations respectively. So this is actually some of the rotations. If we exponent such a part, it becomes a cosine theta and Einstein scales cosine theta and sine theta, and also for the boost, one time component and one partial component. And now we want to deduce some of the commutator relation between the generator. First of all, I will exchange the index. First of all, the alpha beta is now the matrix element, and the mu and the low sigma is the index for the generator. So different kind of the generator. So that if we calculate some of the commutator relation between the mu generator and the itself, and the by using the explicit form of the generator mu and m low sigma, it is expressed by the Minkowski matrix and the Kronecker data. Then we can obtain the commutator relation between m and m. And it is just a closed form. There will be the another generator m with the different index will be turning out with the Minkowski matrix. Now we want to include some of the momentums operator. Actually, also by using the commutator relations of the M generator, also we can obtain the commutator relation between the spin and a booster and a booster and a booster. And by using the linear combinations, such as Lorentz algebras is a homomorphics with the SU2 and SU2. So, if we add the momentums generators, which is represented some of the translations in the Poincare algebra, then we can just add the momentum generators in the transformation. So this momentum generator is the ball translation, and we already know that how can the momentum generators can be represented is just I partial mu's in the quantum mechanics. And now we want to deduce some of the commutator relation between the momentums and the generator M mu. We will use some of the group identity. This is quite simple. There are two parameters. One is the parameters, antisymmetric parameters for the generator M mu, and the translations parameters for the momentum generator. So this is just the multiplications of the two group elements. This transformation is actually the group elements, Poincare group, elements of the Poincare group. And the inverse of the elements also can be obtained. That is just the additional transformations and the inverse of the transformations, x prime to x. So if we consider the such a conjugate form of the group element, that's quite appears many times in the algebra and group theory. So this element is transformations with M mu. So the conjugate acting on the group element which represents the translation. We can expand that each element with infinitesimal transformations from the exponent with the generator, M mu and the momentums and M sigma lambda. And if we consider just the order of the omega and the order of the omega scarcity, then negligible gap, then we can observe that there will be the commutator relations between M mu and the momentum operators will be turning out. So the M mu P is and minus P and M mu, so such a commutator relation will be turning out. And we can calculate this conjugated form of the group element in the different way by using the group identity. So this quantity sort of becomes the this form. Plus, if we calculate the first element and second element and acting the inverse step, then we can obtain that just the expressed by the one group element. Then these parameters with the translation part can be just written by the momentum generators with the parameters with omega inverse and I. And we can relate this quantities again by extending this such Lorentz transformations on the spin transformation form nearby the identity. And if we're using the antisymmetric properties of the W menu parameters, then we can realize the equations by following form. So there will be the momentum generators terms will be appears in the sign, and there are additional terms with the same similar form. And it means that the commutator relation between the M menus and the momentums are written by these closed forms. So there are some momentums generator will be turning out as a result of the commutator relation. So that's the result, M menus and the momentum generators commutator relation. So Poincare algebras can be written by the following commutator relation between M and the momentum, and the momentum itself is equal to G. So it's a closed form. So by using this Poincare algebra, we can obtain the multiplications of any group element in the Poincare groups. That elements generated from this generated by the exponent. Now the remaining topics of the today is the Casmir properties of the Poincare algebra. The Casmir properties are defined as the C-scale such as Casmir properties that commute with any group elements of the algebra or any generators only any elements of the algebra I. The first Casmir properties of the Poincare algebra is momentum scale. So P scale, P mu's, the momentum generators that commute with the P scale so trivially. And if we calculate the M mu and the P scale, also it gives the J. So the P scale is the Casmir operator. And another Casmir operator is the Pauli-Luzobansky polarization vector. which is defines the W mu with antisymmetric tensor epsilons on the momentum and the generated arm, and the W square is a Casmir operator. So to multiply this powerless Lorentz polarization back to scale is a Casmir operator, we should calculate the commutator relations through with between the W square and the momentum and W square through with the arm, generated arm. So if we calculate the P mu and the W nu, there are some of the calculations about it. Then it becomes a zero. So the P mu and the W squares are also the zero. And the commutator relation between M mu and W low, there are some of the quite additional techniques. So such a Pauli Luzobansky's polarization factors are represented by the other form, commutator relation between the M and the P. So by using that, the such amino and the W commutator relations are non-zero, but the commutator relation between the amino and the W scales will become to zero. So the such Pauli Luzobansky polarizations also commute through with all the elements of the algebra. So this is the Casmir operator. It means that the these Casmir operators are represented with the what is the invariant quantities in the algebra. So if we consider some of the math case, then the for the last prime, the momentum can be written like that, and there's such a power Ludovinsky polarization factors are reduced in just spin operator. So that such a W scale is the lattice with the spin scale, and the momentum scale relates to the mass. So the such a mass and the spins the invariant quantities even we ask the space-time transformation by using the Poincare group. So the mass and spins are representations of the Poincare algebra. Also, we can understand such a Casmir operators by using the conjugate form. Next time, I will talk about the supersymmetry algebra, that's extensions of the Poincare algebra. So the in the Poincare algebra, today we talk about the explicit form of the generated arm, which contains the spin and the boost, and also we deduce the commutator relations between the generated arm and the momentum p, and there are also another commutator relations, and we obtain the two Casmir operator, W square and the P square, and we can know that the mass and the spin is the invariant quantities in the Poincare algebra. And in the such algebra, it will be the same step will be following. So we will add the additional generate a supercharge Q, and also we will derive all the commutator relation, and the anti-commutator will be included. And also we will find some of the Casmir operators, which is the invariant quantities in the supersymmetry algebra in the next time.